This might sound a bit complicated. Okay, the basic thing is here in self-contained there is only one coil. Okay, so current is passing that coil, which will produce a magnetic field and a flux, which will link the same coil. And because this magnetic field linking the coil, there will be induced EMF, and the direction of induced EMF will oppose this external, not exactly external, will oppose the source, which is this current. This is also called back EMF. I don't think you have. Okay, that's not important for the test now. At least you just have to remember this one. Input is the current I, output is the flux linkage, and there's a proportionality constant which is L. So in self-contained, the same coil. Current is flowing the same coil, which is producing flux, which is in the same coil. In mutual inductance, current is flowing in one coil. The first coil, you can say I1, and the flux is flowing in the second coil, and the constant proportion is M21. This mutual inductance of 2 with respect to 1. But in self-contained, there is only one coil. So current flowing that coil is producing a flux which is linking the same coil, and the constant proportion is the self-inductance here. Okay, let me check the question. Sir.
Sir, Maxwell equation and energy conserved, sir.
Energy conservation of what? Transformer. Okay, let me go to Maxwell equation.
Okay, sir.
You have to remember those 4 equations because we already studied, and it's not difficult to remember. I'll just tell why. So the first one is Gauss law of electrostatic. We studied in the first chapter. Integral E dot dA is Q by epsilon, but Q is the charge present inside this surface, the closed surface. This dA means elemental area. So this integration is surface integration, and the circle indicates the closed surface. Okay, this is Gauss law for electricity. Similarly, Gauss law for magnetism, it's B dot dA is the charge, magnetic charge is 0 inside the surface because magnetism and alkyl always in pairs. We cannot separate north pole and south pole. So the net charge present inside is 0. Okay, and this is in chapter 6, electromagnetic induction, which says the EMF induced, which is the voltage. The Faraday's law of electromagnetic induction, it says EMF induced is minus d phi by dt, right?
Yes, sir.
And the EMF is another symbol is the voltage V. Okay, so this voltage and electric field are related as minus dV by dr. Okay, gradient of the potential is gradient of the potential, the V is function of R, is the electric field. Okay, so from this I'll get voltage as E dr, actually dV. So the integral over the closed path E dot dr. So this is actually voltage, integral E dot dr. So that's what there's there in this equation. Integral E dot dl, that is the voltage, which is d phi by dt. This induced EMF E this is actually voltage. Okay, that E is electric field. So this is actually epsilon. Okay, so this is actually voltage. You can put this or V. Okay, so don't get confused with that. So what is there here? In this one is the electric field, not the voltage. So electric field dot dl, if you integrate, you will get the voltage. because of this one, because voltage is related to the electric field as this one. Electric field is negative gradient to the potential. This first chapter or second chapter. I think first chapter itself. Okay, from this I get the voltage as integral E dot dr. So the induced,
Sir, if we integrate E dot dl, we'll get EMF, sir.
yeah,
Okay, sir.
this is done in first chapter itself.
Okay, okay, sir.
Electric field and the potential are related by this. So this is actually voltage integral E dot dl, which is d phi by dt according to Faraday's law. Okay, and in chapter 4 we learned this one, Ampere's circuital law. Integral B dot dl is mu naught into IC. IC is the conduction current. But in this chapter, Maxwell introduced this additional term, which is the displacement current, which happens between two capacitor plates. Between two capacitor plates, there is no conduction current, but there is displacement current because of the change in the electric field. Okay, that will produce a magnetic field. In the previous chapter, we learned the source of magnetic field is a current, but here, in addition to current, it can also be a time-varying electric field. So this is a capacitor with the current is flowing with which is changing with as a function of time. But in between this, there is no current flowing. But because the current is flowing, there will be accumulation of charge. The charge here will keep on increasing. And the electric field, which is sigma by epsilon naught, sigma will keep on increasing because charge is increasing. Charge sigma is Q by A. A is constant, but Q is increasing, so sigma will increase. So once sigma increases, the electric field here is a function of time. So that varying function of electric field as a function of time is equivalent to a current, which is called a displacement current. So this I, this is the displacement current, is d phi E by dt, and phi is nothing but E into E. So a time varying electric field will give a current. Okay, that's called displacement current. The current in this wire is a conduction current, but between the capacitor plate is displacement current because of the changing electric field. So that's what he has introduced in this equation. So this is Maxwell's contribution, the second term. Okay, so these are the set of 4 equations.
Okay, sir.
Okay. So what do you ask about energy conservation? See, there is one energy conservation about this transformer. I said the
Yes,
is
sir.
conserved because just because voltage is going does not mean I'm creating energy. Because when the voltage is going up, current will go down by the same factor. So that the voltage product of voltage and current, which is the power, is same. Power is same, means energy is also same because energy is power into time. That is the thing I had as energy conservation, nothing else.
Sir, can you repeat, sir?
See, in the transformer, on the secondary side, if it is a step-up transformer, voltage is going up, right?
Okay, sir.
That does not mean I'm creating energy because when the voltage is going up, current will go down by the same factor.
Yes, sir.
Okay, so the product of the voltage and current will be same. Transformer, I think it is there in which chapter. Yeah. Transformer is there in this chapter. Maybe. Yes, is there in the AC chapter. So, see, here we have primary coil and secondary coil. As I said, the flux which is linking this both primary and secondary is same, which is phi. So if you take just take one term of this primary and one term of this secondary, d phi by dt is same for both. So d phi by dt is same for both primary and secondary. But so whichever has got more turns will have the more voltage across it. So what do you call this primary and secondary will be number of turns of the secondary, which is ns into d phi by dt. Voltage drop for the secondary is ns into d phi by dt, and voltage drop of the terminals of the primary will be np into d phi by dt. flux is same, which is linking both the primary and secondary. So whichever has got more turns, if NS is more, then it's a step up transformer. If NP is more, it is a step down transformer. Okay. So another thing is must be ideal transformer, so there is no energy loss. So the power on the input side should be equal to the power on the output side. Okay. So this should be true because there is no losses. It's an ideal transformer. Okay, that means that from this I'll get this relation IP by S equal to VS by VP, which is NS by NP. So if voltage is going up means current will go down, so that the product of voltage and current is same on the input and output side. That means there is no power generation. I mean, power is same on the input and output side, so energy is also same. So energy is conserved. That's what I meant.
Okay, sir.
Yeah. So any other question?
Or any derivation?
Derivation, we have to show that the power in this pure capacitor circuit or pure inductor circuit is zero, average power.
Okay.
Okay, one is sine, one is cos. So average of sine into cos is sine 2 omega t, which is zero.
Okay.
Sir, what about RLC, sir? LCR circuit.
LCR circuit, you have to the impedance of LCR circuit is R plus J. R square plus XC minus XL whole square root, right?
Yes, sir.
Impedance, sir.
So you have to find out when the power will be maximum. The impedance, just let me. Resonance has gone. Okay. So this is the RLC circuit, no? RC and LR series. Okay. So impedance of this circuit is R square. Where is it? R square plus XC minus XL whole square. Okay. R and actually it will look like this, right? R in one direction and XC and XL are in the opposite directions. So they will combine as XC minus XL or XL minus XC, which is dominating. And this is 90 degrees, so it will combine as a Pythagoras theorem. So Z is square root of R square plus XC minus XL the whole square. Okay, so as a function of frequency, R will not change, but XC is 1 by omega C and XL is omega L. So when I change the frequency, which is the frequency of this voltage source, this is my control, no? So if I change this frequency of this voltage source, R will not change, but XC and XL will change because XC is 1 by omega C and XL is omega L. So if I choose the frequency of particular value, it is possible that this two will combine to give zero. XC is 1 by omega C, so as frequency increases, XC will keep on decreasing. And XL is omega L, so it will keep on increasing as frequency increases. So it is possible for a particular frequency, XC minus XL is zero, that is XC equal to XL. That they have put as reference in here. In reference condition, they have put XC is this one, XL is this one. So at reference condition, this XC equal to XL. Okay, so that means 1 by omega naught C equal to, let that frequency be omega naught. So that particular frequency, XC is 1 by omega naught C and XL is omega naught L. So when these two are equal, that frequency is this one. So in that particular case, this Z will be minimum because this is positive and this is also positive, and this is the only variable, the second one. So whenever this thing becomes zero, Z will be minimum. Okay, so that happens at resonant frequency. Okay, impedance is minimum at
Sir.
resonant frequency.
Impedance is minimum and XL is equal to XC, sir. When it is maximum, sir.
No, maximum can be see what you're going to change. You're going to change the frequency.
Yes, sir.
Okay, that's the only variable. Okay, when frequency is changing, R is not going to change because that's a property of R. But Xc is 1 by omega c, so it will keep on decreasing when I increase omega L, and this XL is omega L, so they keep on increasing as frequency increases. So maximum impedance can be infinity because if omega keeps on increasing, XL will keep on increasing, right? So Z will keep on increasing.
Okay, sir. Understood.
Uh,
Understood.
so minimum
Okay,
means
sir. Understood.
minimum means this is a positive quantity. So the minimum of positive quantity is 0. It's square, no?
Okay, sir. So it
that
will be
happens-
resonance.
that happens is to omega naught.
Okay, sir.
So if you equate this to, I'll get omega naught as 1 by LC. So Z is minimum at this resonance condition and the current will be maximum. And when the current is maximum, the power is also maximum. Because the voltage source is fixed, Vm. Power is V into I. Voltage is fixed, which is not going to change. I'm only changing the frequency. So, and the current I will be maximum at resonant frequency. So power will be maximum at resonant frequency. Okay. Any other question? You know what is wattless current? No.
Yes, sir.
Yes, sir.
Current that is flowing in inductor and capacitor is wattless current. Because the
It is zero now, sir.
because the corresponding average power is 0.
Okay, sir.
So this electronics we should know which is more wavelength, which is less wavelength, and which is more frequency, which is less frequency. Gamma ray is maximum frequency, so it has minimum wavelength. C is same for both any electromagnetic wave. C is 3 × 10⁸ for light. It is also same for X-ray. Also same for radio waves. But if we change the medium, it will change. C in vacuum or air is 3 × 10⁸, which is true for any electromagnetic radiation. Air is X-ray, gamma ray, microwave, radio waves, everything is same. So wave propagation direction is E cross B. Okay, so wave propagation you can find from the function form. If it is sine kz minus omega t, it's a positive z direction. If it is ky minus omega, it is positive y direction. If it is ky plus omega, it will be negative y direction.
Negative.
So once I know the direction of this one, and I know E cross B is the direction of propagation, so I can figure out whether E is along x-axis or y-axis or z-axis. So I can also find the direction of B. And C is E by B. Electric field you learn first, so this first by second. C is the velocity of the electromagnetic wave. Okay, so everything is covered. So if we just revise this concept, only the last 2 things I didn't add previously. There is self-inductance and mutual inductance. Only those 2 points I have to add. So just go through these concepts. You should do fine.
Okay, sir.
Okay, so shall we close?
Sir,
Yes, sir.
given E waveform and find B waveform, what is it, sir?
Yeah, that's what I did in the beginning, right? That B. See, waveform is either E or B. Just a minute. See, these 2 are waveforms, right? This is electric waveform, electric field waveform, this waveform with the magnetic field. Both will have kz minus omega t because both will travel in the same, waves traveling in both. So both is traveling the kz wave. See, here you can see electric field is like this, magnetic field is also the same, right? When electric field is 0, magnetic field is also 0. The only thing in the direction is different. Electric field is on the x-axis and magnetic field is on the y-axis. And x cross y, which is I cross j, which is k, is the direction of the propagation of the wave, that is z-axis. So this is a solution of the Maxwell equation. So this is what I mean by waveform. This is electric waveform for electric field, this is waveform for the magnetic field. Okay, so there is an example here. Here, they have given this is what waveform of magnetic field, right? So once I see this one, I know this is a waveform traveling the negative x direction, right? Because x minus a is positive x. This is x plus a. So this is a traveling in negative x direction, and they have put by. So direction of the magnetic field is along the j direction or positive y direction. So from this I can find the electric field direction as
Sir, can you
Hold on,
show
hold
that
on.
question again, sir?
Yeah, I'll come. So wave direction is minus I cap. Direction of the wave because x plus t, right? Is it
Okay,
clear?
sir.
Okay, and p is
Yes,
on
sir.
j cap.
Okay, sir.
Hold on. P cap is j cap. So you have to find E cap is either k cap or minus k cap. So E cross B, k cross j. What is k
Understood,
cross
sir.
j? Minus I. So this is correct then. Okay, so this is direction of E and not minus k. So I got Ex as some positivity in this one. So once I have this one, I know Ex is that form, and E naught will be this B naught, right? Amplitude 2 into 10 to 7. So amplitude of the electric field will be C times B naught, because C is E by B. So whatever is B naught, which is 2 into 10 to minus 7, that into 3 into 10 to 8 is E naught. Okay, so since By is, once By is given, I know it is Ex. Okay, Ez. Yeah, Ez, right?
K
Yeah.
cap, sir.
Ez. Okay, so it is Ez. It's Ez, and then this amplitude I can get from this one. V naught C. Which is turns out to be 60. And the waveform will be same. Same minus x. You have to copy this one. This whole thing will repeat. There is no change in this one for electric and magnetic field. So here I given this B waveform and I found this E waveform. All right. Simply I can give E and ask you to find B. For electromagnetic, this one E and B are related.
Sir,
Ah,
how will you find B naught, sir?
B naught they have given. Hold on, I'll show.
No, sir. If they ask B naught means how will you, sir?
Wait. What about the question? Just one minute. See, they have given By as this one, right? B naught is amplitude of By. Which
Yes,
is
sir.
okay. This T is Tesla, unit of magnetic field.
Okay, sir.
Okay, this is B naught.
Okay, sir.
It's like a, see, this is sign variation, no? Okay,
Yes, sir.
the amplitude of the sign variation is B naught. Okay, similarly, electric field variation is this one. The amplitude is this one, E60, which is E naught.
Okay, sir.
Okay, this is a variation, no? This is sign variation, the amplitude is V naught. Previously we called it VM, right? IM, similarly. Actually, EM is same as E naught. E naught is amplitude of this EX. And B naught is the amplitude of this BY. This is a sign variation. So maximum value is E naught. And C is E naught by B naught. It's E by B, but these two will cancel, right? These two will cancel. Sign and sign will cancel. So C is E by B, which is same as E naught by B naught. So if E naught is known, B naught is known, other way also. One is known, the other is known. Okay.
Okay, sir.
So just relax. I think you will do fine.
Okay, sir.
We'll close. Others? Yeah.
Yes, sir.
Yeah. Okay, see you tomorrow.
Thank you, sir.
Okay,
Yeah.
sir.
Bye. Bye. Good night.
Sir, come to our venue, sir.
Come for
Our venue, sir.
Purila.
நம்ம எக்ஸாம் ஹாலுக்கு
Okay.
வாங்க
Okay.
சார்.
Yeah, I'll be there.
தேங்க்யூ சார்.
Yeah,
குட் நைட்.
sure. Yeah. Good night.
Right, sir. Good night, sir.